complicated, it's really not. All it does is it takes the picture and divides it up into macro blocks, which is a fancy way of saying 16 by 16 pixel blocks. That's it. And then for each of those blocks, it tries to figure out where they've gone, frame to frame. Simple as that. So in this case, it's saying, well, this block moved there, and that one, and so on and so on and so forth. So what we wind up with is a whole bunch of x, y vectors, saying this block went here, that block went there, so on and so on and so forth. There are limitations to this. It's very crude. It's an entirely two-dimensional array. It's not trying to work out what has actually moved in the scene. So if you have a person scrolling across your scene, it is not going to tell you that person scrolled across that scene. It's going to tell you this block looks like it went over there. Not necessarily. There are certain effects that may make the block seem to skip all sorts of effects. If I, for example, move across here, it might decide that this sort of pocket here looks very similar to the pocket while I move over here. So we'll say, oh, good job. It's not right, but that doesn't matter. For you in TV land watching, it looks right, and that's all that matters. It doesn't matter that it is right. So you have to take the motion vector data with a pinch of salt. It also won't pick up certain types of motion. For example, this incredibly complicated looking scene down here is the motion vector estimates from a scene in a movie. Anybody guess what it's showing? What that frame? Sorry? No, not explosion. No, that is the camera moving forward.
Oh.
So as the camera moves forward, the motion vector in the middle sort of moves a little bit, and the motion vector on the outside moves a lot. But see, it's a matter of interpretation. The motion vector isn't telling you that. It's just telling you these blocks moved here. It's up to you as a human to go, well, that means the camera moved forward. So it's quite difficult to interpret what these motion vectors mean in code. But thankfully, we don't care about that. We're just doing motion detection. And better for us, the camera's going to stay still. So we don't have to worry about it. All we have to worry about is there movement in the scene? And given that we can assume the camera remains still, it shouldn't be too difficult to sort out the motion as a curve. Look for some vectors and see if there's enough for a larger. Should be simple, right? So, what do we actually get? What does the Poise camera give us in this new version? It quite simply gives us a whole string of data which is organized as an x vector, a y vector, and a SAD value. A SAD value, sum of absolute differences, not a particularly depressed value. What this means is it's trying to say how good it thinks its estimate of the motion is. So if the sum of absolute differences of the vector is 0, it means I know precisely located where this block has gone in the image. So it's a very good match. But sometimes its best match for where a block has gone is not so good. And in that case, the sum of absolute differences will be large. As it happens, we're not going to deal with that now. We're not interested in SAD values, we just want the data. X, Y, that. So we'll just concentrate on that, keep it simple. So the code looks slightly complicated in as much as we read all stuff in the buffer and convert it to the data types, and you know what, forget that. New version of Blockcode does all the tedious stuff for you. So all we have to do, this just instantiates the camera, gives it a resolution, starts recording. We're going to say record step enough, because we don't care about the video. Use the H.264 encoder, send the motion return to a special output. This is simply a subclass of PyMotion analysis, new feature in the new version, which will call analyze for every frame. And A is just the array of vectors. Simple as that. It sorts it all out for us. Gives us a NumPy array, two-dimensional x, y vectors, say D values. Let's see it. This is where everything goes horribly wrong, by the way. So, here's our little camera. And I'll just print out the array for every single frame. Yeah, there we go. And there's the array given. Lots and lots and lots of vectors. For about 10 seconds or so. Okay. So you can see tons and tons and tons of arrays. And we've got X, Y, SAD. X, Y, SAD. As I was waving my hand in front of it. X, Y, SAD. Not very good SAD value there, but there's our data. X and Y. We don't actually care about horizontal or vertical as far as detecting motion is concerned. All we care about is the magnitude. How do you calculate the magnitude of the XY vector? Anybody? curious, yes? Absolutely. Square root of the sum of 2 squared. Pretty simple stuff. Square the x after, if I think it's with float, because otherwise things go wrong. Square the y, square root, flip it to a pi, because that's easy and simple. And then let's just print the maximum to see what the biggest vector we had was. See what happens with that. Good. You actually see it doing things. So, small vectors, big ones. Yep. This is basically down to noise of the image. If you look at a raw frame, you can take a still from the device camera through the still board, but actually does is take a whole bunch of frames and average them together, and you get a lovely smooth photograph. You take just the one raw frame, it's quite noisy. Right. If you look at all those, especially in dark lighting, you get a lot of noise. This camera is ramping up the exposure. You get speckles all over the place, so when the motion vectors go, oh, it's going over there and over there, and all sorts. The trick in those particular cases is to work with sound values and to figure out where these sort of motions are occurring. If it's all over the scene, probably isn't one entity of the scene. It might be something else. A little more complicated. But, can we do a little better than that? Histogram. NumPy has a lovely histogram routine, so we can take all the vectors in our particular scene, which we've calculated the magnitudes for, and say, let's bin them. Let's put them into, well, I've got 10 bins here. Put them into 10 equally sized bins, and then we'll divide it by the check by 6, so we want 1 to 6 for each one, and then we'll print that. There's a bunch of hashes, which the syntax highlighting thing is a column. So let's try that. Efficiency. Fair enough, I'll try to do that. Oh. Aha.
So the faster you move your hand, the more that takes.
Yep. There we go. Jumping into different bits. So there's all sorts of refinements that we can do to this. Putting it into different size bins, classifying it by that, drawing a shape around the features. So yes, all sorts of future work for people to play with. This is a very, very quick, crude demonstration. So those features of motion, convex hull, convex hull. Especially drawing a line around the points to say, okay, all my points sit within this boundary. So if you could take out all the big motion vectors in your scene and say, draw a line around that. Okay, that's one area as opposed to all of it. Probably not noise. Is it big enough to be a human? Quite useful in my particular case is a cat who has free reign of the house. So doing motion detection while the cat's wandering around is not a great idea. My alarm system is useless for me. I'm also playing around with this, I think one that's slightly more useful for me. Feature labeling is another interesting one, very similar to classification you were talking about in machine learning, where you have individual clumps of things, and there's a function in Solidity that will do this again automatically for you. Fast enough on a Raspberry Pi? Maybe not. But it allows you to label clumps individually. So there is a clump, there is a clump, there is another one. Which one I might want to go, there's Dave, there's a cat. Fun stuff. So, very simple. Lots to go and play with there. I urge everyone to go and play with it and build something incredibly cool like this. Oh, we can build a sea and what's up there. I don't know. Very enterprising chap, got very sick of the cats pooing in his garden and decided to use Vigo Reliability with his Raspberry Pi and a little motor attached to a sprinkler. The sprinkler, as it happens, is down here-ish. Mr. Pussycat is about to have a bad day.
Immediately commercialise the system would be a lot.
Oh, we can't see any of those. Just jumped off and it's brilliant. Oh, there. Yes. Sensor, Raspberry Pi's up here, and there's the sprinkler.
very sensitive. It can't basically determine know whereabouts the motion on our screen, so you can calibrate it over us to.
There was a very, very interesting project I saw the other day, not involving the prize camera, but very, very similar stuff, whereby somebody had rigged up an airsoft rifle to a rig that would do motion tracking and lead the fight. But moreover, it had also put in a system whereby you would notice colours in the scene, and if you waved a particular flag over this colour, it wouldn't shoot you. So he sort of wanders in front of it and things starts firing like he brings out this orange shirt. And you go, oh, brilliant. Yes. There's any number of things you could indeed do. The motion vector data, because it's all calculated on GPU, as opposed to CPU, it's incredibly fast. Chucks it over to the CPU, at which point you get to play with it in OpenPy. So the Pi is currently being described as a whacking great GPU attached to a tiny CPU. And that's more or less accurate. So getting the GPU to do all that encoding, excellent. That's the bulk of the work out of the way. And now you can play around with it in admittedly relatively slow way, very, very quickly and easily.
Yeah.
Well, that's it there. Play away. Thank you.
Yeah, but yeah, no. Okay, okay.
Excellent.
No, I do. Okay. Thank you all.